C, which is hybrid Monte Carlo or Hamiltonian Monte Carlo. Hybrid Monte Carlo is the original name from gauge theory, and Hamiltonian Monte Carlo is just the same, exactly the same algorithm, but for statisticians. And I'm going to talk about it on manifolds, but HMC is a very, very general method that works on obviously vector spaces, manifolds, but also Hilbert spaces, so even in infinite-dimensional spaces. And so the goal is to construct methods that sample distributions. So if you consider that we have some target P, so if you have a target distribution P, so a priority measure on a manifold M, so you assume it's a known optinormalization constant. So you don't actually know the normalization, but you write it into this form, where vol is some kind of reference measure on your manifold that you need to decide. And the goal is that you want to generate samples from the distribution. So I actually don't know what sampling really means, but for me what it means is that you want to create a sequence of points, xi, or random variables, such that you're going to essentially approximate your distributions by a discrete measure. So, for example, if you want to approximate a distribution, you need to have a metric and or a type of convergence. A typical type of convergence on probability distribution is narrow convergence or weak star convergence. And what that means is that here you see you have a discrete measure parameterized by n, your number of points, and you want to approximate the integral of some observable f with respect to p without some kind of discrete measure, so discrete integration of f. So if your discrete measure converges, so if your sequence of discrete measure converges to p narrowly with convergence, that means that this is gonna converge to this for all bounded and continuous functions. So that's what it means to approximate expectations. And so in the case of distribution of manifolds, those are very common in applications. So in statistics, often you have you consider Fisher-Bingham distribution on Stifel manifolds. So for directional statistics, for example, that's very, very common. So Lemkuller and Leliev do a lot of research on canonical distributions which arise in molecular dynamics. And often those are on holonomic manifolds, which are just manifolds which are just basically a subset of the Euclidean space with some constraints. And in statistics, you also often, the covariance matrix is very important, and you also look at distribution on the space of covariance matrices, or its complex generalization. And so, for example, there are papers where you use that to learn the spectral density matrix and things like that. And in gauge theory, you're interested in discrete actions, which are also something you need to integrate over a Lie group. So that's kind of the setting. So you want to approximate your target distribution with some discrete measures. And so the idea, so one of the ways to do that is to use mechanics. So most people are, so here we're going to assume that the minus log density of your target is a potential energy. That's essentially the mechanics interpretation of sampling. And so if you were in Euclidean space, you would propose moves using basically Newton mechanics. So this is a way to propose new points to approximate your measures. And when you're in a manifold, you do the exact same, except you need to introduce the curvature of your manifold in your equations. So you start from Newton equations, and you end up with Riemannian Newton equations. So it's just acceleration, so gamma would be your solution of Newton's equation. Acceleration is equal to derivative of v divided by m, and that's exactly the same on the right-hand side, except you have the Riemannian generalization of these operators. That's very nice, because if you do that, what you can show is that the solution of this system preserves these distributions. So that's a distribution on what's called the tangent bundle. So the tangent bundle, if you're not familiar, if M was a manifold on which your target distribution is defined, your tangent bundle is basically just a set of velocities. So these little arrows. So it's a point and a velocity. And so the reason why that's nice is that mechanics preserve this distribution mu, but the projection of mu onto your manifold, so your tangent bundle is over your manifold, is exactly your target measure P. So the point is that you use mechanics, you propose samples that's gonna define a measure preserving transition kernel, and you're gonna get essentially exact samples from your target distribution. So that's the idea of mechanics. Your flow preserve mu, and projection of mu samples are P samples. So if you were able to do mechanics exactly, you're done. The problem is that you cannot do mechanics exactly. And so that's where the theory of numerical integrators for mechanics comes in. So instead of solving your mechanics exactly, you're going to use some kind of approximation. So here I denoted psi of dt. So your dt is just a numerical time step. So you replace your exact flow on your exact solution on the velocity space with just some discrete approximation. Now, the question is then what properties does this need to have? That depends on exactly what you want to get, but to end up with this algorithm, you need these two properties. You're going to need this reversibility constraint, where S just means you're flipping velocities, the sign of the velocity. And you're going to need this requirement that it also preserves that volume, which was introduced here, which was related to mu, which is a reference measure of mu, which is the symplectic volume form. And if you do that, then this algorithm gives you a way to sample from a target distribution. So it's very simple. You're at some kind of velocity at the nth stage. You just apply your numerical integrator, you get a new point. And you accept this new point with this probability, which is related to the energy difference between your initial point and your final point. If the point is accepted, that's your new configuration, and if it's not, you reject it, but you just flip the sign. That's what it means. And so that's what we call MDMC. So this is MD, you do some molecular dynamics or some Newtonian mechanics, and then you do MC, so you do some Monte Carlo accept-reject step. And that, you can show, does preserve your target distribution. And so, for example, an example of numerical integrator is the geodesic integrator. So you can see here, what's happening here is that your geodesic integrator follows the geodesic on the sphere. So here you go from the purple point all the way around to the blue point. Then it changes velocity using in an appropriate way. And then you follow again the geodesics. And that way give you point on the sphere, which you're going to approximate distribution of the sphere. So here if I follow very long geodesics, and here if I follow very short geodesics, but it's the same thing. So this is your geodesic integrators. But now you do have a problem of ergodicity. So ergodicity just means that you want to explore your sphere or your manifold well. So you want to propose points which are kind of representative of your target distribution in the manifold. And the reason why you have an ergodicity problem is that essentially if you have a good numerical integrator, you want the energy difference to be very small, because otherwise most points get rejected. But if that's true, then that means that you stay essentially on the level curve of H. So, essentially you want your energy difference to be small, but if it is small, then that means that you're not exploring very well, because you're staying essentially, if you started with this energy, then you're staying somewhere here. So you do want to have a way to deal with this ergodicity problem. And what you do is that you introduce what's called a heat bath. So you're going to change your energy level. And you're going to add that to MDMC. So the HMC is just MDMC with a heat bath defined by just a Gaussian. This just means that the covariance matrix is given by your Riemannian metric. So essentially, all that does is you do MDMC, then you generate a new velocity that's going to change completely your energy level. So you were here, you're going to end up here. And then you're going to do a new MDMC, and then you change your energy level, you end up here, you do a new MDMC. And that helps you a lot to deal with your ergodicity problem. So HMC is just MDMC with a heat bath. And so there's other heat bath you can take, and for example, Lamcular used this kind of process, where you can see these two things here are my normal Hamiltonian mechanics, and this thing here is a heat bath, so that's what changes your energy level. And those are used a lot. So this is essentially a OU process that changes your energy level, and this is a Hamiltonian system which preserves the energy level. So there's loads of different types of heat bath, but the point is that you have a MDMC and a heat bath, and that's HMC in its very general sense. So I just want to show you HMC in practice. So this is actually how so this is what typical HMC process looks like. So you can see one of the nice things about HMC is that the points that appears are not very close to each other. So they're actually quite distant. So that's one of the nice things. You avoid the random walk behavior of some standard algorithm. So, okay. You continue.
So these points are computed by your trajectories?
Yeah, exactly. So here I have a distribution which is which is given by the color. So where it's very red, it's a very high mass, and where it's blue, it's very low mass. What I do is I follow the geodesics on the sphere, I change the velocity, and I follow the geodesics on the sphere, I change the velocity, that gives me a proposed point, and then I accept, reject, depending on energy difference. And that's our rendering. So that's HMC.
So it's one step. Every one step, you have 1 point.
Every one step of HMC, you do have a point, but it depends then, the number of geodesics and velocity change you do depends on your actual mechanical integrator. So you might have many, or you might have very few steps. But the point is that you define a mechanical integrator that gives you a proposed value, and then you accept, reject. And then you refresh your heat bath, so you change your velocity, and then you do again, MD, MC, and so on. So that's basically.
Can you explain again why it's important to have this Hamiltonian part as well? I mean, why it's important to preserve or to stay on the energy level in one part of integration, and then to do the heat bath?
Yeah, so in the MTMC step, so that's before the heat bath, you want your energy to be as preserved as possible, and by energy I mean H, so the function H, because you can see that your new proposed point is accepted without some kind of probability. And if the energy difference is very high, this probability becomes very low. So essentially what happens is that you propose like very distant point, but they're always rejected. So that means that your actual approximation is just the same point all the time.
But you cannot have something which is really exactly energy preserving, because then you're then it will be just the same result every time, this probability, right?
So if you add something which is always energy preserving, which is impossible, for something I'm going to say after, your new points will be always accepted. So that would be very good, actually.
My point was just that the reason why you do symplectic integrators is that you want to preserve volume. That's the reason, right?
You want to you want to preserve volume. That's what it means, and you need that for this to be true. So that you need, and then you can ask yourself your question. Yeah, but I also want energy to be preserved.
Yeah, then
that's not
this
possible.
barrier. So
that's not possible. So there's a theorem which I'm going to discuss now. Essentially, that's HMC, and now we're going to discuss integrators. So okay, so now we have these two requirements here for just this thing to be defined. So for this algorithm to be true. But now you can ask yourself, well, I have a mechanical process. I would like to have an integrator that also preserves at most the most it can about the mechanical system. And for example, something you want to preserve are energy of the system, symmetry of the system, or the symplectic structure. So we know that we want the integrator to preserve the symplectic structure for the thing to be defined. And then we can ask the question, can we also have energy preservation? That's impossible. So at least it's impossible to have all three. And normally when you have this preservation, you also have this one, because most integrators that we use are variation integrators. I'm going to come onto that later. And if you have those two, you cannot have that one.
But isn't it so that you would like to have the volume preservation, and the symplecticity is a way of getting that?
Yeah. Yes and no.
So yes,
so yes, because in principle, you only need that. So in principle, you only so what I mean by symplecticity is this. And that implies volume preservation. So in one way, you could say, I just want symplecticity to have volume preservation. There's two things to note. One is that to have a volume preserving integrator, it's usually easier to build them using symplectic integrator just in practice. So that's just a practical thing. But most importantly for HMC, this is actually much better than volume preserving, because this property is going to imply the existence of a shadow Hamiltonian. And so what that means is that, so people which are familiar with modified equations, when you have a true ODE, and you have a numerical approximation of your DE that defines a numerical trajectory, and you can ask your question, is there another ODE which is closer to my approximation than the true DE was? So you have true DE, numerical DE, and then you ask yourself, is there another ODE which is actually closer to my approximation than the true ODE? So that's a modified equation.
But why is it interesting for the definition?
So I'm going to come to that. So the point is that, actually, wait, sorry, what did you ask?
Why the modified Hamiltonian is?
Yes. So the point is that the existence of this nearby shadow Hamiltonian implies that your acceptance rate, cannot imply, in practice, your acceptance rate remains high for long distance proposal. So because what happens is that your shadow Hamiltonian is very well preserved by the numerical trajectory. So that's one thing. And then you have a separate thing that your Hamiltonian and your shadow Hamiltonian are actually very close in terms of energy, or as close as you want, which means that essentially your energy will be well preserved during the numerical integration. So that comes only from the shadow property, not from the volume preservation property. So
how does this play with the heat bath? Because you're changing the energy at every.
That heat bath is separate, because I have a heat bath that defines my initial condition. Then I'm going to do MDMC, and the energy is at the end of the MDMC step.
And then your step is quite long. Your trajectory.
Ideally, I want the trajectory to be very long, and if I have the shadow property, I also know that my energy difference will be small, so I have a high acceptance rate. So basically, that's the idea. You want to propose a very distant point to reduce the correlation between samples, but you also want those very distant points to be accepted. And the shadow Hamiltonian helps a lot in that. So the existence of the shadow helps a lot in that. There's also a paper that actually
we call it a modified Hamiltonian.
Yeah, so shadow Hamiltonian for people, for other people is modified Hamiltonian. So up to you how you want to call it. I think shadow is only really from the H theory that calls it shadow. I don't know in molecular dynamics what
it's
name.
fine to say shadow.
Oh, yeah, okay, yeah.
It's just different
Yeah.
communities.
Okay, so basically, yeah, your shadow Hamiltonian is exactly your modified Hamiltonian. So it's basically it's if you consider the shadow Hamiltonian as Hamiltonian, you calculate its flow. That's going to be much closer than your numerical integrator than your original system was. So it's a better approximation of your numerical integration, and that implies that your acceptance rate remains high. So the theory of the integrator, so how you build these kind of integrators, which are very nice, is very, very, very large. From the Hamiltonian perspective, the basic method is what's called the splitting method, which means that you have your Hamiltonian, which is essentially a sum of a kinetic energy and your minus log density target. And what you do is that you do a numerical integration for this and this separately. So that would be a typical splitting method. Or your V, you can decompose into V1 plus V2, where say V1 is very expensive to compute and V2 is very easy to compute. And then you can have a splitting which splits the kinetic energy, which is a geodesic flow, easy potential and a harder potential with different time steps. So that would be a typical splitting method. That's the Hamiltonian perspective. Then you have the Lagrangian perspective of similar integrator, which the idea is that mechanics can be defined either through Hamiltonian or through Lagrangian systems. And you want to create integrators which basically use the same physical principles as your original system. So a Lagrangian system is defined by a least action principle. So it's just you want your action, you want to vary your path and you want your action to be stationary, that's the word, stationary with respect to variations. And you want to do the same with your discrete Lagrangian. So you're going to discretize your action, discretize your Lagrangian, and build a variational action principle for this discrete theory. And what you end up is essentially you have the continuous Lagrange equation, and then you end up with discrete Lagrange equation. And what those have is that not only they're symplectic, but they're automatically symmetry preserving. So if your original system had a symmetry, and your discrete approximation also has a symmetry, then the integrator has the symmetry as well. So it's very, very nice. And then essentially these variational integrators are part of the largest theory of integrators, as an integrator, which is the theory of generating functions, which essentially tells you, okay, if you actually want a symplectic map, then you have that this map is symplectic if and only if something, and that something requirement defines some generating equations. And I'm not going to go into detail of that, but that's the kind of most general theory of integrators. Right, so just quickly on the origins of HMC. HMC arises in lattice QCD, and without going into details, the point is that you have a Lagrangian which describes quantum chromodynamics, which is the theory of gluons and quarks, essentially. And you have, so that's the continuous theory, and then you want to discretize that give you lattice QCD, so your space-time become discrete. And what you end up is with this kind of partition function for lattice QCD, and you want to actually calculate that integral, but that integral is actually an integral over the Lie group SU3. So you can still look at the details here, but the point is that you end up with a Hamiltonian. So basically you end up with something you want to integrate, and you add some fictitious momentum, which lives under the algebra, and that's basically the origin of HMC. So I just wanted to say that, because that is the true Riemann manifold HMC. So the original HMC is actually already on Lie groups with a non-constant metric. Essentially, your metric is going to be the Cartan-Killing form. So although people in statistics call Riemann manifold HMC Girolami's work, HMC was originally already a Riemann manifold HMC. I wanted to emphasize that.
What does it mean, QCD again?
Quantum chromodynamics. Just, it's Yang-Mills theory, basically. So basically in physics, you like to describe things in terms of curvature. So Einstein came up with general relativity to describe gravity in terms of curvature, and Yang-Mills theory is about doing the same for all the other forces. So you have QCD, QED, and all that. Okay, so just very quickly, this is the way that originally Kennedy and Rossi defined mechanics on SU3, because once you know that you want to do it over SU3, you need to actually have a way to put mechanics. What they did is that they came up with this symbolic structure, which defines some Hamiltonian equation, and then just use that. And that's nice because here there are no coordinates set up here. So these are just your dual frame. These are just momentum coordinates. These are just the algebra constant. I don't want to go into that much detail, but the point is that that's the way they did. They came up with a symbolic structure, and then they said that's going to be my symbolic structure, and I'm going to demonstrate mechanics with it. So this is just the origin. So now this is what people in statistics call Riemann manifold HMC. And right, so here your point is that you're using the Bayesian setting. And so your target distribution is actually some posterior distribution. So here W is my data, and theta is parameters over which my posterior is defined. And the idea is that you want to define a Riemann metric which locally matches the Hessian of your posterior. So that's the Hessian of my posterior. And if you average that over data, so if you do that, you end up with this thing. So this is just the Hessian of the prior, and this is essentially what's called the Fisher information matrix. Okay. So here I wrote it this way because this is the true Riemann and Fisher metric, which is an actual Riemann metric on a statistical model. Mm-hmm. And this is the matrix that comes out of it once you parameterize your statistical model. So when your statistical model becomes a statistical manifold, your true Fisher Riemann metric becomes the matrix Fisher metric, which is no longer positive definite. That's something important for HMC. But okay, so you decide this is going to be my metric, and hopefully it's actually a metric. And then you define, so what came up out of this is that you're essentially your target Hamiltonian as this form. And this is the correction term that Leliev mentioned yesterday. The reason why you have that is because when you do HMC with a geodesic flow, what you end up targeting is a measure whose reference is a probability distribution, whose density is with respect to the Riemann volume form of that geodesic flow. But when you're in Euclidean space, you don't actually want that Riemann volume form, you just want the Lebesgue measure. And so you have to introduce this correction term, which ensures that you're not targeting the density with respect to the Riemann volume form, but just with respect to the Lebesgue density.
So does it mean that you are pulling back the distributions from some space to a parameter space?
Yeah. Yes, it's something we can go over details later, but that's what it is. So you have a statistical manifold, which is essentially related to your likelihood, and that's a general statistical model. So it's just a set of probability measures. But then you want to parameterize that with theta, and that pulls back your statistical model to a parameterized statistical model. And if that map is not an immersion, then this thing is not a metric. And that's something, because usually people introduce the Fisher information basically already as a matrix. That's fine. But the point is that when you're doing HNC, you definitely need this to be invertible. And this might compromise its invertibility. So it's worth distinguishing between the true Fisher-Riemann metric on a set of probability measures and the parameterized Fisher-Riemann metric information matrix, which might not be positive definite. Okay, so so you end up, how much time do you have?
5 minutes or so.
Okay, perfect.
A little more.
Perfect. So
You go until 50 if you
Well,
want.
I need to set
Yeah.
up too, so.
Yeah, but we delay five minutes, I think, because it's my fault. Yeah, we go into the coffee break.
Okay. As much time as you need. You only have 2 more slides, right?
yeah, exactly. So it's just, okay, so basically, so just to summarize, so you have HNC, you want to use mechanics to sample from a distribution. One way to do this is with your geodesic flow. That's a very good way to do it when you can, which is not the case in linear dynamics, which is why yesterday Julia had introduced this rattle scheme, because essentially you actually cannot compute the geodesic flow of your metric, and so you need to deal with constraints. Right, okay, and then, and originally it comes from lattice QCD. In statistics, the geometric aspect of HMC became famous when Giolami introduced the statistical model of HMC, so when he brought information geometry into HMC. So that's what this is. Something to note here is that here your Hamiltonian, you actually don't know the geodesic flow of your Fisher metric. And so you need to find a way to integrate it. So originally, Giolami did that with the generalized leapfrog integrator, which is just an integrator that is applicable to any Hamiltonian, separable or not.
What's it called?
Generalized leapfrog integrator.
Uh-huh.
It's from the perspective of discrete Lagrangian, it's just leapfrog constrained to some manifold.
Done by you.
We put it in our book. I think it was the
Yeah, you
first,
put it in your book, yeah.
first place it was mentioned or named that.
Okay.
And,
okay.
and we had just an aside, since we have a little time. Sebastian and Reich and I, when we were discussing that, we thought, should we give it a name? And we said, well, why not? And it now has like hundreds of citations. It's just a very simple idea. I mean, it's like a basic method.
Is it implicit or is it explicit method?
It's implicit.
It's implicit.
It's just a generalization of leapfrog, but it was a very natural method.
Yeah, but it's a good idea.
So actually then there's 2 methods that are from Imperial which are interesting with this setting. One is that one, generalized leapfrog, which is just leapfrog for constraint system, essentially, when you view it from discrete Lagrangian theory. But there's also another paper with Patrick.
Right, that's what I thought.
Exactly, no, that's why I said it, because I thought you were thinking about that. So that's a paper which is very, very useful for manifold HMC. It says, okay, so I have a Hamiltonian, the potential energy represents my target, and then I have a kinetic energy, which essentially is a way for me to travel through sample space in an efficient way. But often I cannot compute the geodesic flow of that kinetic energy properly. But what if I can compute some other geodesic flow? And that's often the case, at least in statistics. So this is very often the case. And what you end up is with an integrator which uses that other geodesic flow to give you a simple integrator. It's still implicit, but it works for any manifold.
Because you have 2 metrics in
Exactly,
that paper, right?
If they're proportional, then you end up with just, so if your kinetic energy is proportional to the geodesic flow you know, then you end up with an explicit method, which is essentially leapfrog. And when you don't, you end up with an implicit method. But the point is that it works for arbitrary kinetic energy, for arbitrary manifold, as long as you know some geodesic flow. And that's something that he proved using the theory of generating functions as well. So you build a generating function, I think you impose symmetry to have reversibility, and then you end up with something. And it's particularly useful for homogeneous manifold. So in that paper you talk about symmetric spaces, because then you have a very natural geodesic flow, and so you end up with something a bit simpler. But okay, so those are 2 things you can do when your Hamiltonian is non-separable. When you're in Euclidean space, it's a recent paper as well that uses the fact that you can lift your Hamiltonian, you can add a dimension and create another Hamiltonian, which can integrate exactly, and whose projection was the Hamiltonian you cared about. So there's another way. Right, I'm going to skip the last comments. Okay, so then this is things I've done with Tony Kennedy. So the point is then to use the theory of mechanics with symmetries to HMC. So the point is that in statistics, so in general, we know that H-epsilon Lie group is very nice for many, many reasons. And we want to ask the question, what about the manifold which are Lie group quotient by another Lie group? And so what we did is that we say, well, we can view every potential energy on M as a potential with symmetry on G. And that's basically the main idea. So the point is that we're going to simulate our Hamiltonian mechanics on M using mechanics with symmetries on G. So the point is that we do everything on G, and then we quotient by K, and then we have our result.
But don't you depend on, you have to be careful then of what you do on G so that it descends on the...
Oh yeah, very. You have to be very careful. But it's very easy to be careful though. but yeah, you do. So the point is that the symmetry, so basically we have a manifold, M, is of the form Lie group over Lie group. So one way to view it so it's a quotient space. And so the point, so we view every potential energy on M as a potential energy with K symmetry. So essentially we have an action of K on G, and our potential is invariant with respect to K. The action defines a momentum map. Now, for your Hamiltonian system on G, to descend to a Hamiltonian system on G mod K, you need to basically stay on the level set J minus 1 of 0. So here you would have your motion in G, and if you stay on the level set J is equal to 0, then you end up with a genuine Hamiltonian system on your sphere. So here is a big difference between HMC and mechanics. In mechanics, if you had a system here on G mod K, if you pull it back to G, you have a degenerate system. But we don't in HMC, because what we do in HMC is that we pull just the potential energy, and then we define a new non-degenerate energy on G, which is a genuine kinetic energy. So we have a genuine Hamiltonian system. And the way we impose the constraint...
the potential energy is just depending on the position?
Yeah, exactly. And the way we impose the constraint that you should stay in your level set is very easy. You say that initially it's on your level set, which is just setting something to 0. And then because you have symmetry, it always stays on J is equal to 0. So essentially, this thing is very important. You need to actually stay on J is equal to 0, but that's very easy because of the symmetry. So if you stay, so the point is, so the point is that you reduce HNC on G mod K to a problem of HNC on Lie group, which is very, very easy. And essentially for any geodesic orbit manifold, you can use the fact that your geodesics are essentially given by Lie group exponential. So you Lie group exponential, just something under the algebra, which is a vector space, and then you reduce, and you have a genuine Hamiltonian system in your sphere. So you can see here, even for hyperbolic spaces, we stay exactly on the manifold without any constraint, without anything.
Which kind of homogeneous manifolds are you interested in?
All of them. So, or more specifically, so geodesic orbit manifold are something more useful in string theory than in statistics, but it has a subclass which is called the space of naturally reductive manifolds. And so I think maybe you know where this geodesic orbit manifold comes from, because it's one of your colleagues in Edinburgh.
Oh yeah.
Yeah, it's from Jose Miguel Sierra. Yeah. So you were studying these kind of things. Yeah. And on natural reductive spaces, you have essentially you have a very nice properties of your geodesics. And the point in that is that this family includes Stifel manifolds, so hypersphere and all of that. It includes Grassmannian manifolds. It includes all compact Lie group.
All symmetric spaces?
It includes all symmetric spaces, including, therefore, the space of positive definite matrices and the space of Hermitian positive definite matrices. So basically, most manifolds that have a name are actually in the class of natural reductive manifolds. But the problem, so that's really actually very nice for statistics. And my point is you have to be, it's much more useful for statistics than, for example, for molecular dynamics. So there's 3 hours of HNC, and that's going to be my last comment. There's essentially the gauge theory literature, the molecular dynamics literature, and the statistics literature, and they have different problems. So in the gauge theory literature, your manifold has been set since '87. It's SU3, and so your geodesics are you know exactly all the manifold thing. So it's all about numerics. Since in the last 30 years, all of the gauge theory HNC is just about numerics. In molecular dynamics, it's very, very different because basically every system is a new manifold. Every system has its own kinetic energy. You don't, that manifold doesn't have a name, that manifold doesn't have, that kinetic energy doesn't have a geodesic flow, which you know. And that's why, that's the link with what we did yesterday. So when you're not in a nice manifold with a name, you're gonna have to do something much more related to what we explained yesterday. So you're gonna have to use some basically constraints to deal with that. But here, for this class of manifolds, you know the geodesics and you have global coordinates because they're Lie groups. So they're totally geodesically embedded into GLN. And so essentially for statistics, this solves those two problems, the geodesic flow and coordinates. And yeah, and that's it.
Thank you very much for the very nice talk.
Yeah.
Yes, one question.
Yeah.
No, sorry. Before me, the others. Do you have questions? Yes, some.
With the Lie group setting, is there a natural way of trying to do the tilting thing we talked about a bit yesterday? Or is that only really working you putting into it?
Oh, right. So you mean have an exponential family and then
Using representations or something? I'm not really sure.
well, okay, so actually, in general, I mean Lie group. So usually they're matrix group.
Yeah.
But actually, it's true that in QCD you're interested in arbitrary representation, even if they're a matrix group. So you do end up with basically Rn. So I guess in principle you can have an exponential family there easily. But I haven't thought about it more. But basically, when you're in a Lie group, you're basically in Rn. So normally things that you can do there, you can do in a Lie group. And actually, just one thing I wanted to mention about your comments about staying on J is equal to 0. If you, for what me and Kennedy wanted to do, you need to stay there. But you can think about this much more generally in terms of just mechanics with symmetry. When you don't stay on J is equal to 0, you introduce an electromagnetic field. And that's not a bad thing, actually. So there are papers of HMC in which you do use a magnetic field to decrease your correlation between samples. So to end up with Rn with a magnetic field, you just do Rn mod S1.
Yeah.
You introduce some charge that you want to conserve. So you're no longer in J-1 of 0, you're in J-1 of mu. And when you reduce, you end up with Rn plus a magnetic field. So it's not necessarily a bad thing, but you have to be very careful to make sure you're still preserving your target measure. So you need to think of a bit. So if you do it properly, you do.
Yeah.
But in a general manifold, your reduced space is some kind of.
There is another question.
Oh yes, sorry. Yeah.
So I will know.
Very fast. So in this, on these manifolds, generic manifolds, molecular dynamics.
Yeah.
What method would you use? Something like symplectic integrator with the.
So if you're just on a, so if you're on a submanifold of Rn, what you would, which does have a geodesic flow, you have two possibilities. Either you use Lankudder's method, in which you use another geodesic flow to help you, or you use Luriel's method, in which you do some kind of rattle scheme, and you need to make sure, so in practice you need to make sure your reversibility, because remember reversibility was a constraint on our integrators to make sure that it makes sense. So you need to have,
Still want symplectic?
what, sorry?
You want symplectic?
You want, yes, okay, let's say you want symplectic and you want reversible.
Reversible?
Yeah.
And constraint?
Yeah, yeah, so I'm assuming assuming you satisfy the constraint, then you want reversibility and symplecticity.
Okay, we have a coffee break later, and there will be a nice discussion in the coffee break. Thank you very much.